Okay, this last one should be short, much shorter than the last one. What we're going to do is this time, instead of writing a Taylor series polynomial centered around 0, we're going to center it around somewhere else. Example, again, what we're going to do is in the first video where we centered it somewhere else. So here's an illustration where we're doing centered around 0, and we did first order, third order, and a fifth order polynomials. We saw how close it was. Now we're, instead of centering it here at 0, we're going to center it somewhere else. Today we're going to focus on this particular example is going to focus around centering around pi over 2, which is here, and the transition to change that occurs when we do that. It just simply moves the center, allowing it to be more accurate around a certain spot. So we want to be accurate around pi over 2 here in this case, and we're going to use this function sine x. Steps are pretty much the same. I'll show you the parts that are different. The first step is derivative step, and what we do is we need a 0, 1, 2, 3, 4, and we take the derivative of sine. The first one is 0 derivative, so it's just sine x. Then we take its derivative again, cosine x. Take the derivative of cosine x, you get negative sine x. Derivative of negative sine x is negative cosine x. And the derivative of negative cosine x is sine x. Now we need the value. Here's where it's different. We need the value of the derivative at pi over 2, because we're changing the center. So now we take sine of pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. Negative sine of pi over 2 is negative 1. Then 0. Sine of pi over 2 now is 1. As we start becoming periodic, it starts repeating itself. Alright, so we have the derivative component. The next component is the coefficient part of this. We need the number in front of the x terms, and to do that you need to do the coefficient is you need to divide by the factorial part. The first one is 0, so you divide 1 divided by 0 factorial, 0 divided by 1 factorial, negative 1 divided by 2 factorial, 0 divided by 3 factorial, and then 1 divided by 4 factorial. And to simplify, we create the coefficient of, now 0 factorial is defined to be 1, so this is 1. That's 0, so that's going to be a disappearing term. That's negative 1 over 2 factorial. I'm going to leave the factorial there. 0, then 1 over 4 factorial. Those are my coefficients. Now let's write the polynomial. So the function sine x is equal to, as long as I do an infinite series, coefficient 1. Now here's the difference. Now instead of taking x subtract 0, we're going to go x subtract pi over 2. We're translating over to pi over 2 to the 0 power, plus 0 plus negative 1 over 2 factorial x minus pi over 2. Now that one would have been to the 1, this one is square, plus the 0, plus the next one is positive 1/4, 1 over 4 factorial, x minus pi over 2 to the 4th. We skipped those because they're zeros. So simplifying it, oh sorry, if I'm going to put equal, I better put dot dot dot. So equals 1 minus 1 over 2 factorial x minus pi over 2 square plus 1 over 4 factorial x minus pi over 2 to the 4th. plus dot dot dot, and now we can write our nth term by looking at the pattern. If I want to consider the sequence, I want to start at 0 and go to infinity, then I have to look at it this way. The first value I plug in is going to be 0, and I want to get that. I want that to be my 1 and that to be my 2. So each time I need to see how that works. So the factorial part, this is 1, that becomes 2 factorial. 2 becomes a 4 factorial, so it's doubled the n value. So I'm going to write 1 over 2 to the n factorial times x minus pi over 2. That's the same each time, but now this is also doubled the term. So it's going to be 2 to the n. This is the exact same thing as sine x because I created an infinite number of terms in my polynomial. Now, we're going to use it real quick to approximate. So if I wanted to approximate this value, sine of pi over 4, now we can find the exact value in our calculators, but that's not really even exact. That's using a better order Taylor series polynomial. That's what calculators do, is they use these polynomials. So this is approximately equal to, now I want a second order. That means I need to look for the second power. So I'm going to stop right there. This part right here is my second order. That's leaving me with an extra term here, which would be my Lagrange error, and all the rest of it is my truncated error. So sine of pi over 4 is equal to 1 minus 1 over 2 factorial x, which is pi over 4 minus pi over 2 square. Now if I compute that, I get my approximation to be 0.6916. Now the error, we express errors as a positive term, so we take the error is equal to the actual sine of pi over 4 minus the error, my Taylor series polynomial, which was this. And if I compute that, I get an error of 0.0155. The Lagrange error is to compute the very next term in the polynomial using that pi over 4. So the Lagrange error of that computation would be 1 over 4 factorial, 1 pi over 4, subtract the pi over 2 to the 4th, which gives me a Lagrange error of 0.0158. Notice again, Lagrange is a heavy hitter. It's the very next term. The very next term holds most of the error, as you can see. Only the error gets slightly smaller when I consider the full error. So we like those Lagrange errors. That's it for today. You want to practice, so obviously there'll be book problems and stuff for you to do. Again, I miss you.